Okay, in the last video, we talked about how weather is caused by small disturbances in the atmosphere, which occur as part of the global scale redistribution of heat from the sun. Okay, so our first observation is that heat from the sun is not distributed evenly across Earth's surface. We want to think about why that is. There are two main reasons why heat from the sun is not distributed evenly across the Earth's surface. The first reason is something called the angle of incidence. The angle of incidence is describing the angle at which sun rays are hitting the surface of the Earth. So we'll want to remember that the sun is many times bigger than the Earth. So we can think of, sunlight coming from the sun. It's all kind of coming from one orientation, kind of straight on like is shown in this figure. But when it strikes the surface of the Earth, it's going to hit it at different angles because the Earth itself is curved. So this figure is showing sort of little flashlight beams of sunlight coming from the sun and hitting the Earth. And you can see that around the equator, these little flashlight beams of sunlight are striking the Earth and making these nice little circles here. But as you move to the north and to the south towards the poles of the Earth, you see that the same amount of sunlight is sort of spread out over a larger area, as shown by these more oval shapes in the north and south poles. So if each one of these beams has the same amount of energy coming from the sun, then the question we want to ask ourselves is, what area is that amount of energy being spread over compared between the equator and the poles? So for simplicity's sake, let's just say that each one of these beams has 1 watt of energy coming at them. 1 watt, units of energy. Okay, great. Now we can say that, all right, each one of these beams down by the equator is going to have this 1 watt of energy sort of spread out over the area of a circle. And the area of a circle can be described as pi times the radius of that circle squared. So let's say this is a circle with a 1 meter radius. So it would be 3.14, which is pi times 1 squared, and that's going to equal 3.14 meters. Meters squared. So here we would have 1 watt of energy spread out over 3.14 meters. 1 watt per 3.14 meters squared. That would be sort of at the equator here. But up at the poles, we get a ruler. You can see that the same amount of energy, that 1 watt, is being spread out over this larger area that's shown by this ellipse or this oval, right? So you can see that it's about 1.5 millimeters. So let's just say that's going to be 1.5 meters, right? So the equation for an ellipse, the area of an ellipse is pi times its long axis times its short axis. And so if we say that that's going to be 3.14 times 1.5 times 1, and we can tell right away that's going to be a larger number. It's going to equal about 4.7 meters squared. Okay, sorry about that, getting kind of cramped on the edge. All right, so up at the poles, this same 1 watt of energy would be spread out over 4.7 meters squared. Right, so it's a smaller number. It's a smaller amount of energy. It's being spread out over a larger area, at the poles, the north and south pole compared to the equator. So sort of sum up this angle of incidence idea. energy from the sun is spread over a larger area at the poles than at the equator. And that should be than at the equator. This means that the equator is usually much warmer than the North and the South Pole, which we sort of know intuitively, right? We picture the equator, we think of tropical places, the Caribbean, Bahamas, right? Really beautiful, lush, warm places. And when we think of the poles, we think of reindeer and Santa Claus and penguins, right? So poles are very cold, in part because of this angle of incidence idea, that the energy from the sun is sort of spread out over a larger area at the poles than at the equator. Okay, now the second reason is related to this angle of incidence idea. The second reason that the poles are colder in general than the equator is this thing called albedo. Albedo is the percentage of incoming solar radiation that is reflected rather than absorbed by a surface. Okay, albedo, the reflectivity of a surface, or the percentage of radiation that's reflected rather than absorbed. This thing called albedo is sort of determined by two features. First being color, second being, I'm going to reuse this term, angle of incidence. Okay, so everybody knows that if you wear sort of a black t-shirt on a hot sunny day, you'll be a little bit warmer than if you wear a white t-shirt, right? So white, or light colors in general, sort of reflect more light and absorb less heat energy. So that means that light surfaces on the Earth and any other sort of celestial body will reflect more light than dark surfaces. So light light-colored surfaces reflect more light. Okay, now this angle of incidence idea, you can imagine that light coming in at an angle like this to the poles is more likely to bounce off of the surface of the Earth and reflect back into space, kind of like skipping a stone off a surface. You want to have a nice low angle that the stone hits the surface of the water with. It's more likely to reflect. But then sunlight that comes in and hits dead on like it does at the equator, much more of that energy is likely to be absorbed. So another way to think of that, we can draw this sort of over here in this space. So we've got a surface, the sun's very high in the sky, right? A lot of energy is coming down and striking very directly onto the ground. Let's say it's, like a parking lot, it's midday, the surface is gonna get really, really hot. Something like 95% of the sun's energy might be absorbed by that surface, and a very small amount, like maybe 5%, might be reflected. But similarly, very early in the day or very late in the day, right, when the sun is low in the sky, coming in at an angle, much more of that light is likely to be reflected, bounced off the surface, maybe something like 33% might be reflected, and something like 67%, not 667, 67% might be absorbed. Okay, there we go. So these two basic principles of the angle of incidence causing the energy from the sun to be spread out over a larger area at the poles than it is at the equator, and the idea of albedo, the idea that not all of the sunlight that comes in is absorbed by the Earth, but some of it is reflected, and more of it gets reflected at the poles because it tends to have this low angle of incidence, right, where the sunlight is striking the surface, at an angle, just like skipping a stone on a pond. It bounces right off. So those two ideas cause the equator to be much warmer than the poles at any given time.